All right, welcome to today's lecture on Chapter 14, Fluid Balance and Blood Health. Here are the key objectives we'll cover in this chapter, and I will mention which one we're covering as we go along so that you can come back to this video and search for the particular objective that you want to go back over. I also recommend that you go ahead and pause the video and intake it at intervals so that you don't sit here and watch the whole thing all at once and sort of dissociate and so you can take in all of the information at your own pace. So these are the 11 objectives. Let's go ahead and get started with learning objective 1, which is to identify extracellular, intracellular, interstitial, and intravascular fluid. All right. In this section, we're going to break down the two major fluid compartments in the body, intracellular and extracellular fluid. These are super important to understand so that we can understand later on how our bodies maintain balance and function. First, let's start with intracellular fluid. So, as that name suggests, this is the fluid inside of our cells. It makes up about 2/3 of the total water in our body. So, the majority of the water in your body is actually found inside of your cells. Now, let's talk about extracellular fluid. This is the fluid outside of the cells, and it accounts for the remaining 1/3 of water in the body. But that is divided into two main compartments. The first is the interstitial fluid. This is the fluid that sits between the cells within a tissue. It's like the water that bathes and surrounds all of your cells, helping with nutrient exchange and waste removal. And the second is the intravascular fluid, which is found in blood and lymph. This includes the plasma in your blood that circulates nutrients, hormones, and waste products throughout your body. Together, those fluids play essential roles in maintaining balance within the body, supporting everything from nutrient transport to waste removal. And so, in the next section, we'll dive deeper into how the body keeps these fluids in check. This is just showing a visual representation of what we discussed on the last slide. So feel free to pause if you'd like to take a little deeper dive into this image. Okay, moving on to learning objective 2, identify the functions of electrolytes in the body. So let's talk about how the body balances fluid levels, focusing on the solutes such as electrolytes and ions that are crucial for maintaining health of our bodies. Let's start with ions, which are, if you remember, charged particles that play a significant role in our body's functions. And ions are categorized into two types: cations, which are positively charged because they've lost an electron, and anions, which are negatively charged because they have gained an electron. In intracellular fluid, which is again the fluid found inside the cells, the major cations to worry about are potassium and magnesium. Those are essential for various cellular functions we'll talk about, but those include muscle contractions and nerve signal transmission. The major anion in the intracellular fluid is phosphate, which is vital for energy production and cell signaling. Moving on to the extracellular fluid, which is again fluid outside of the cells, find different major ions. Sodium being the predominant cation here, it's going to play a crucial role in fluid balance, nerve function, and muscle contraction. And then chloride is the major anion, which helps maintain the body's acid base balance, aids in fluid movement, and is essential for the production of stomach acid. Let's move on to the next slide. Right, you see here is the graphical breakdown or sort of table breakdown of the information that we just discussed on the last slide. So again, feel free to pause this down and copy it into your notes. Okay, next we'll discuss the functions of electrolytes in our body. Electrolytes are minerals that carry an electric charge and are found in your blood, your urine, your tissues, and various other body fluids. And they're going to be essential for a wide range of bodily functions. But let's talk about a few of them. First, they are vital in maintaining fluid balance and the distribution of water between the ICF, the intracellular fluid, and the ECF, the extracellular fluid. And that balance is important so that you can regulate your body's hydration levels as well as the various cellular functions, which we'll discuss in more detail in the next slide. Second, electrolytes play a key role in the transmission of electrical impulses through the neurons. This is crucial for numerous functions, from triggering your heart to beat or enabling you to read, or move your arms. And so the movement of electrolytes through the nerve cell is going to actually help the cell carry electrical impulses across the cell membranes of neurons down the axons and out the axon terminal. And the third thing here is that charged minerals are critical in muscle contraction. Electrolytes like calcium, potassium, and sodium will help trigger contractions that move the muscles in your body. This includes not only the muscles that help you move your limbs, but also those that control vital functions like your heartbeat and your respiration. All right, as promised before, let's get into the mechanisms that maintain the balance between intracellular and extracellular fluids, which is again important so that your cell can just function and maintain the normal body's processes. Water distribution between the two compartments is really highly controlled, and it's highly controlled through the concentrations of the various ions that we've been talking about. And in order to balance the fluid levels, you got to make sure that you also maintain your ion distributions. And so central to that process are things that we call transmembrane pumps, which are proteins that pass the cell membrane, and they actively regulate water volume and electrolyte concentrations in each of the fluid compartments. One key player that you'll hear about a lot is the sodium potassium pump, which moves ions against their concentration gradients. This particular pump um, moves sodium ions out of the cell while maintaining potassium ions coming into the cell. And that's a process that requires energy in the form of ATP, since when you're moving particles against their concentration gradients, that's not going to be normal. And that's not how physics normally works. And so, in order to do that, you're going to have to put in some energy. And so, that would not be considered passive, but rather active transport. Following the movement of those ions, water then moves via osmosis from areas of low solute concentration to areas with a higher solute concentration. And that movement is essential so that you maintain cellular equilibrium and ensure that your cells do not shrink or swell excessively, which would obviously be detrimental to their function. Here you see an image of the sodium potassium pump at work. So I'll give you a chance to pause here if you want to read all this information. But you can see the big takeaway is that you are utilizing ATP so that the sodium will diffuse away and the potassium will diffuse into the cell. All right. We're going to discuss learning objectives 3 and 4 now. So on this slide, you can see what might happen to a animal cell. In this case, it's a red blood cell when it's placed in various solutions. So on the left side, in a hypotonic solution, which is a solution that's going to have less solute than the inside of our cells, what happens is water rushes in and may cause the cell to lyse or burst. In a hypertonic solution, all the way on the right, there are more solutes outside of the cell, so you can see that the cell shrivels or crenates due to the loss of water. And only in an isotonic solution, where solutes are equal on either side of the cell membrane, do we get an equal movement of water, or what we might call no net change in water levels. And again, if you're not quite sure what that means that the amount of water that moves into the cell is equal to the amount of water that moves out of the cell. I always tell students to, for example, if you had $10 in your bank account and you paid for something that was $10, but then immediately put $10 more back into your account would stay at $10. That would be no net change. Okay, now let's talk about how the bodies regulate fluid balance, and let's particularly focus on the kidneys because they're going to play a very pivotal role as the main regulators of this system. If water take is insufficient to replace our losses, our blood becomes concentrated with those solutes, and the blood pressure may fall. And so this scenario would trigger the body to go into conservation mode of water, and it'll initiate a complex response involving several hormones. One key hormone that we want to talk about that's involved in this process is ADH, or antidiuretic hormone. That's going to help the body retain water by reducing the amount excreted by the kidneys. Another critical component is the renin-angiotensin system, and that system begins with the release of renin, which is an enzyme that catalyzes the production of angiotensinogen into angiotensin 1. Angiotensin 1 is then converted into angiotensin 2, which is a vasoconstrictor that increases blood pressure and stimulates the release of aldosterone from the adrenal glands. Aldosterone then further aids in water retention by signaling the kidneys to reabsorb sodium while excreting potassium, leading to an increase in water reabsorption, volume, and blood pressure. And just as an interesting side note, alcohol, when you drink it, can inhibit the secretion of ADH. That would thus lead to increased urine production and a subsequent decrease in the body's water levels. That's why alcohol consumption can sometimes lead to dehydration and that nasty hangover the next morning. Here's an image of the ADH hormone and how it acts. So if you want to pause to read this, you can. And here's an image of the renin-angiotensin system. All right, so let's move on to learning objectives 5 and 6. All right, let's get into the essential functions of water in the body. Water is not just something we consume to quench our thirst, although that's important, but it also plays a vital role in various physiological processes that are really important to maintaining our health. Firstly, water is fundamental in maintaining the blood volume, which is necessary, of course, for the transport of nutrients and oxygen throughout the body. And that's critical for all the cellular functions and the overall vitality of the person. Water also contributes to the production of various bodily fluids like saliva, which aids in digestion, or tears, which protect the eyes, bile, which helps break down fat, and amniotic fluid, which cushions and protects a developing fetus. Again, water also acts as a lubricant within our joints, ensuring smooth movement and reducing the risk of joint pain and damage. And it also serves as a solvent in metabolic processes, facilitating the dissolution and reaction of biochemical substances. This allows for efficient biochemical reactions within the body. Another thing water will do is it also keeps our tissues moist, particularly in our sensitive areas like the eyes, nose, mouth, and skin. And that moisture will help protect these tissues from damage, and it also facilitates their proper functioning. Participating in chemical reactions, water is also involved in hydrolysis, where it breaks down compounds, aiding in digestion and other metabolic processes. And it helps to regulate your body temperature by the processes of perspiration and thus evaporation. Water helps dissipate excess heat and maintains a stable internal temperature. Finally, water is also essential for the removal of waste products through the urine. Our body excretes toxins and waste minerals, with water acting as the vehicle for those substances. Another interesting thing to say about why water is so useful is that water has a high specific heat. What that means in general is that you have to put a lot of energy into water to raise its temperature by 1 degree Celsius. So the definition of high specific heat or specific heat is the amount of energy it requires to raise 1 gram of a substance by 1 degree Celsius. Now, you actually probably know this already without even having to think about it, because you probably heard the statement before, or the saying that a watched pot never boils. And essentially, what that means is if you're looking for something to happen, it'll take a long time. But if you've ever tried to boil water and maybe you were just really hungry and you really wanted these noodles to be finished, well, when you look at that process, this actually takes quite a while. You would think it might not, because you got the heat turned up all the way to 10. Still takes a long time for that pot of water to boil. The reason for it is it takes a lot of energy in order to move those molecules fast enough. Now, this can help us because when we move around, we expend a lot of energy, we're doing a lot of work, we produce heat as a byproduct. And heat can be damaging to our bodies. But luckily, our sweat, which is made up of a lot of water, takes all that heat. And when it evaporates, it cools our body down. And it thus protects our body from the potential damages that it could face from that heat. Let's talk a little bit about water, the molecule itself. Water is a polar molecule, since it's created from 2 polar covalent bonds, one on each of the hydrogens bound to that oxygen. Since a polar covalent bond leaves one end of the bond slightly more negative and thus the other more positive, Water as a whole, as an entire molecule, actually has an entirely slightly negative side and a slightly positive side. Now, water molecules interact in this way through hydrogen bonding, where the negative side of one molecule is attracted to the positive side of another. This leads to water's properties of both adhesion and cohesion, where adhesion is where water sticks to other things, like water gets you wet, and cohesion is actually when water molecules stick to each other. So, I guess by that definition, yes, indeed, water is wet. Okay. Let's move on to the next slide here and talk about urine. Functions of water waste removal. So that's going to be urine. Urine helps us to remove waste products from the body. Without enough urine production, you're at risk for all kinds of disease like kidney stones. And you typically can output 4.5 to 8.5 cups a day of urine. But that can easily change in response to your fluid intake and your protein intake and your sodium intake. And if you get below that 2.5 cups a day, that's when you're at risk for some potential problems like kidney stones. So where do we get the water? Well, of course, beverages would be your primary source of water intake, but they could also provide a variable number of calories and micronutrients, and so that makes the choice of beverage important, so that you maintain your overall health. For example, if you're drinking a bunch of sugary, sweetened drinks like um, you know, regular sodas and things like that, yeah, they taste good, but they can also significantly contribute to obesity and cardiovascular diseases because they've got a high sugar content. And so consuming those drinks in moderation would be crucial to maintaining your overall healthy lifestyle. And contrary to popular belief, caffeinated beverages, if they're consumed in a typical amount, do not lead to dehydration. And so those beverages can contribute to your daily water intake just like any other non caffeinated drink. However, again, like I said before, alcoholic beverages present a different issue because they'll increase urine output because they stop the release of ADH, and that can potentially lead to dehydration and again, that nasty headache in the morning. In the United States, there is a common misconception that bottled water is safer than municipal tap water. However, both sources are highly regulated to ensure the safety, and thus bottled water does not necessarily offer a safer alternative to tap water. And a little known fact, some of that bottled water is just tap water, and you're paying a lot for it. All right, so here are some popular drinks you might like and their associated caloric content. Remember, it's always better to avoid drinking your calories as these can lead to weight gain, and if you're not careful, they certainly will. And they also don't really contribute to satiety. So you're going to be drinking these and you're still going to be hungry for food. And so that obviously just increases your overall caloric intake. So maintaining, non-calorie providing beverages is probably the better option. And of course, you can enjoy these in moderation. This is just a graph from MyPlate showing water content of various foods. Again, many times when you're looking at foods that have a higher water content, they also might lead to increased satiety. For example, lettuce, that's a very low calorie food and a very high water content food. And so that would lead you to maybe need to eat less of the caloric foods in order to feel more full, more fast with less calories. Now, water needs are not a one size fits all thing. They're going to vary significantly based on several factors. That'd be like how large your body is, the level of physical activity you do daily, your surrounding environmental conditions, and even the types of food you consume. So, the Institute of Medicine provides guidelines for adequate intake of total water, which includes all beverages, foods, and even metabolic water produced by the body. And so they say for adult men, the recommended intake is about 15 cups per day. For adult women, it's approximately 11 cups per day. And so it's really important to understand that our water needs are met when the water inputs from both food and drink balance out the water outputs. And that includes water lost through all of the various bodily functions. In a healthy adult, typical daily urine output ranges from 1 to 2 liters. But urine only isn't the only way that our bodies lose water. As you'll see on the next slide right here, you lose water through your sweat, and that's both visible perspiration and invisible perspiration because you are constantly perspiring, and through our respiration, like when you see your breath when it's cold, that is because there's a water content in that breath, and you also lose water through your feces. Um, what is one really simple way to determine if you're adequately hydrated? It's to look at the color of your urine. They say clear pee is happy pee. So if you are anywhere sort of below 1 or 2 on that scale, you probably need to drink some water. All right, let's move on to learning objectives 7 and 8. Okay, so in order to continue, let's get a working definition of dehydration. Simply put, it's when fluid losses exceed our fluid intake, and that leads to a fluid imbalance in the body. Now, dehydration has a number of potential causes you can see listed here. Obviously, maybe the most identifiable ones would be like if you're exercising or it's really hot or you live in a dry environment. But also, if you just simply have a fever, or you might have diabetes, or you have a burn, or you're vomiting, or you have diarrhea, those will all cause increased water losses. So, and to compensate, you'd like to increase your water intake. Um, Aside from urine color, some other physical indications of dehydration are shown here. And as you can see, they progress from rather mild to rather severe at the bottom of that scale. Like many other things, it's possible to have too much of a good thing. And in this case, too much water leads to something called water toxicity. Water intoxication develops when kidneys cannot remove water at a rate that's fast enough to maintain our fluid balance. And again, this leads to sort of mild to rather severe results. One rule of thing in life that doesn't really have anything to do with this class is that most of the world does not live like we do in the United States of America. Our water use far exceeds our needs. A sizable portion of the world lives in a water scarce environment. And that's due to the things listed here, but also from, in my opinion, one of the weirdest values in our world, which is heavily manicured lawns. The amount of water that it takes to maintain lawns in sort of arid environments is absolutely wild. So if you don't feel the need or maybe even the requirement to have a nice, green, well manicured monoculture lawn, look into other options and plant naturally occurring plants that don't need lots of water. It looks nice and it's better for the environment. All right. So now we're going to move on to talking about the element sodium. Sodium's chemical formula is Na, and this mineral is going to play an important role in a lot of different bodily functions. Those include fluid balance, nerve transmission, and muscle function. In our diets, the primary source of sodium is going to be table salt, sodium chloride. A single teaspoon of table salt provides somewhere around 2,400 milligrams of sodium. And interestingly, most of the salt we consume, about 70% of it, already comes in our processed and restaurant foods. And this really is going to highlight a significant role that food manufacturing and dining out play in our overall sodium intake. Only about 10% of our sodium intake comes from sodium that's naturally present in foods. Another 10 to 15% comes from our own cooking and the salt that we might add right at the table. If we were to consume only unprocessed foods and added no salt to our meals, our daily sodium intake would be dramatically lower, probably only around 500 milligrams per day. Now, the recommended intake of sodium ranges anywhere from 1,500 to 2,400 milligrams per day, and most of us probably far exceed that number. So, if you're someone who's diagnosed with hypertension, it's recommended that your intake of sodium be much lower, and a good goal would be for everyone to strive to not exceed 2,300 milligrams per day. But I encourage you to track that and see how far you exceed it, because I'd be willing to bet that you do. All right, let's talk quickly about how sodium functions in the body. It's going to play an important role in maintaining water balance, like I said. If sodium levels get too high, the body retains water to help dilute this concentration until the sodium levels normalize, ensuring proper cellular function. In addition to water balance, sodium is crucial for the absorption of nutrients in the small intestine. It helps in the absorption of glucose and certain amino acids. Those are vital for energy, and they're the building blocks of proteins, respectively. Sodium is also important for normal nerve and muscle function. Nerve cells rely on the movement of ions, including sodium, across their membranes to help them generate electrical signals. These signals are obviously important for muscle contractions and just transmitting nerve impulses throughout the body. This function is based on the electrical charge created by the shift of sodium and potassium ions across cell membranes. This movement is critical because it helps you conduct electrical charges that power nerve impulses and those muscle contractions we just mentioned. Almost all the sodium in the body is consumed and absorbed through active transport in the small and large intestines. This is localized in the sodium potassium pumps. These are sort of the premier pumps in the body. And honestly, they probably account for somewhere around 50% of your total daily energy expenditure. Have you had you just laid in bed and not moved a single muscle all day? 50% of the calories that you expend just to keep your body going is found in the use of those sodium potassium pumps. Now, since sodium is really just so prevalent in our diets, deficiency is rare. It can occur in some instances, though. So, for example, if you're sweating excessively and you're not replenishing through a sports drink or something, or if you're very sick and you're vomiting, you're having diarrhea, low sodium levels are referred to as hyponatremia, and the symptoms are listed there. On the other hand, excessive sodium levels, hypernatremia, is fairly common. Remember, the goal should be around 2,300 milligrams, and most of us are going to far exceed that number, including myself. Risks of that include high blood pressure, heart disease, and stroke. So you really do want to maintain the recommended daily intake of 2,300. Okay, moving on to the next mineral of importance in the body, potassium. Potassium's chemical symbol is K, and it's a cation. If you remember, that means that it will readily give up its electron and hold a positive charge as a result. Like sodium, potassium is crucial for normal cell function, but it also plays a unique role in cardiovascular health. One of the key functions of potassium is to help blunt the effects of high sodium intake on blood pressure. By promoting the secretion of sodium and water, potassium will help maintain normal blood pressure levels and support overall cardiovascular health. Additionally, potassium suppresses the renin-angiotensin system, a hormone system that regulates blood pressure and fluid balance. This action will further aid in controlling blood pressure and it will prevent excessive fluid retention. Potassium is found in many of our most commonly eaten foods, including fruits and vegetables and meats, dairy, and grain. Adequate intake for potassium is 2,600 milligrams per day for women, 3,400 for men, and most adults probably need to increase their daily potassium intake. So, again, I encourage you to track yours to see where you fall. When it comes to the absorption of potassium, like sodium, it's done mostly in the small and large intestines. Most of the potassium in our bodies is found in the intracellular fluid, and the balance is achieved through the kidney excretion and retention. Potassium deficiency is called hypokalemia, and it can be quite serious. You can see that there are all kinds of potential issues listed here. Now, excessive calcium intake is called hyperkalemia, and it too can be life threatening. It's generally rare in healthy individuals, but for those individuals who might have impaired kidney function, this is a real concern. All right, on to another mineral, chloride. Chloride is an important anion. Remember, an anion is a negatively charged ion because it's gained an electron. Chloride is designated by the chemical symbol Cl. It's the primary extracellular anion, and it plays several key roles in maintaining physiological stability and health. Again, it's the predominant anion in extracellular fluids, so chloride will partner with sodium to maintain fluid balance. This partnership is essential for regulating the amount of fluid in the blood and tissues, ensuring that your cells function properly. Chloride is also vital for nerve impulse transmission. It works alongside other electrolytes like sodium and potassium to create electrical gradients necessary for the propagation of nerve signals, which are crucial for muscle function and sensory processing. In addition to its role in hydration and nerve function, chloride is a key component of hydrochloric acid in the stomach, your stomach acid. And that's, of course, important for digestion as it helps break down food and absorb nutrients. And it also serves as a defense against pathogens that may be ingested with the food. Chloride also contributes to immune function and the maintenance of acid base balance. That's important for maintaining your body's pH level. The balance supports overall cellular function and metabolic processes. Almost all of the chloride in our bodies comes from table salt. It's absorbed in the intestines along with sodium, and most of the excreted chloride would be found in the urine. Now, while rare, deficiency in chloride or hypochloremia is possible if you are very ill and you have a poor diet. The upper level of chloride is 3,600 milligrams per day, and this could contribute to high blood pressure if it's exceeded. All right, now we're on to learning objective 9, where we're going to talk about blood components. Blood is, of course, a very important fluid in the body, and it's comprised of two primary components, each playing crucial roles in bodily functions: the plasma and the blood cells. Plasma makes up about 55% of our blood's volume and is primarily water, which acts as a solvent for carrying other components. It contains a variety of electrolytes that help regulate the body's pH, maintain cell membrane stability, and they carry charges that are essential for muscle and nerve function. Plasma also transports proteins like clotting factors, which are vital for blood coagulation, as well as nutrients that feed tissues and organs throughout the body. And then the blood cells are divided into three main types. Each of them have a distinct function. Erythrocytes are the red blood cells. They're the most abundant cell type in the blood, and their primary role is to transport oxygen from the lungs to tissues and to carry carbon dioxide back to the lungs for it to be exhaled. Leukocytes are the white blood cells, and they're important for the immune system. They defend the body against both infectious diseases and potential foreign materials. And finally, platelets, while they are not blood cells, they are parts of the blood, and they are small sort of cell fragments, and their best known role is blood clotting. When a blood vessel gets injured, platelets gather at the site of the damage and form a clot to prevent blood loss as much as possible. All right, now we're moving on to our second to last objective, number 10. Okay, here is how we classify various blood pressure levels. And it's important to note here that normal blood pressure is anything less than 120 over 80. If you are above that number, 120 over 80, we classify that as hypertension, and 1 in 3 adults have this. Now, risk factors for hypertension include age, ethnicity, obesity, physical inactivity, poor diet, type 2 diabetes. And that's a big problem because that high pressure in the arteries can damage them and affects target organs like the heart, brain, kidney, and eyes. And that's going to increase the risk of heart attack, stroke, dementia, kidney disease, and vision loss. So if you're worried, here are a few lifestyle modifications that you could use to decrease your blood pressure. Number one, of course, being lowering the body weight. The second thing, though, is that you might want to follow something called the DASH diet, which we'll see more info here. The DASH diet stands for the Dietary Approaches to Stop Hypertension. It's an eating plan that focuses on eating foods that can help lower blood pressure and improve your cholesterol levels. The DASH diet emphasizes eating fruits and vegetables, whole grains, lean protein, low fat or free fat dairy. And it also is a diet that is rich in magnesium, potassium, calcium, and fiber without needing supplements. This diet's also going to be limited on saturated fats like full fat dairy or fatty meats, and oils like coconut palm, palm oil, and palm kernels, sugar sweetened beverages and sweets, and also sodium. The DASH diet is going to recommend eating no more than 1,500 milligrams a day per day of sodium. So the DASH diet was based on research studies conducted by the National Heart, Lung, and Blood Institute, and it's similar to other dietary patterns that promote cardiovascular health. Here are some other lifestyle modifications you can implement that'll help you lower your blood pressure, increase your aerobic physical activity, of course, decreasing the sodium, and also limiting alcohol consumption. Finally, there are various pharmaceutical options for folks who are interested in lowering their blood pressure. You do not need to memorize those pharmaceuticals, but you do need to be aware that there are multiple options for medical intervention of hypertension. All right, and now we're on to the last learning objective, number 11. First, we want to identify the major food sources, deficiency symptoms, toxicity symptoms, and functions of iron, and then we'll do so for the rest of them that are listed there. Okay, iron is essentially it's an essential mineral, and it's available in two primary forms in our diet: heme iron and non-heme iron. Heme iron is derived from hemoglobin and myoglobin, which is found in animal products like meats and beef and poultry and fish. And it's well regarded for its high bioavailability, meaning it's more easily absorbed and used by the body compared to non-heme iron. Non-heme iron is found in plant sources like vegetables, grains, and nuts, as well as in iron supplements. But non-heme iron is less bioavailable. It means the body absorbs and utilizes it less efficiently than heme iron, but it's still a vital source of iron for individuals who do not consume meat. In addition to those sources, cooking with a cast iron pan, for example, it might increase the iron content of food, and that's especially true if you're cooking with acidic foods like tomato sauce, for example. That'll increase the amount of iron transferred from the cookware to the foods. Here's the image representation of heme iron, and it's again part of hemoglobin and myoglobin. It's actually what allows them to transport oxygen. Iron is, again, it's a critical mineral that plays several essential roles. We talked about oxygen transport, energy metabolism. It's involved in the production of energy as a component of several enzymes that are engaged in the TCA, or the tricarboxylic acid cycle, or the citric acid cycle, and also in the electron transport chain. Um, both those are part of the cell respiration system. It also helps to metabolize drugs and alcohol. It's part of neurotransmitter synthesis, and it is useful in immune function. It helps with the proliferation and maturation of lymphocytes and the production of natural killer cells, which are integral parts of the immune system and help protect your body against infections and disease. Iron absorption and metabolism in the body involve several intricate processes I'll talk about now, but it primarily occurs in the small intestine and involves various proteins and transport mechanisms. So first, iron is absorbed into the small intestine through carrier-mediated mechanisms, which are specific pathways that facilitate the movement of iron into the enterocytes, which are, again, the cells lining the intestine. So how do you do this? Well, ferritin is the first protein that is inside of the enterocytes, and ferritin can bind iron, and then it'll serve as a storage protein that'll sequester that iron within the cells and regulate its release into the bloodstream, and that'll prevent excess iron from causing harm. Ferroportin is the only known iron exporter protein in enterocytes. It transports iron in its ferric form out of the enterocyte. And once it's outside of the cell, iron is bound to transferrin, a transport protein in the bloodstream. That protein circulates in the bloodstream and transports iron to various parts of the body. And cells that need iron have transferrin receptors on their surface. Those receptors bind transferrin and internalize it through a process called endocytosis. Now, lysosomes will then break down transferrin, releasing the iron for use. The free iron then can be utilized for just various functions like synthesis of new proteins, like enzymes, and hemoglobin, for example. Where do you store iron? You can see here in this image, ferritin and hemosiderin will take up excess iron that's not immediately needed, and it's stored in the liver, bone marrow, and spleen within proteins, ferritin and hemosiderin. Those storage forms of iron can be mobilized when the body needs it, such as for new red blood cell production. All right. Iron absorption in the body is influenced by a couple various factors, including how much iron is currently in the body, the dietary intake, and the form of iron that's consumed. The percentage of iron absorbed adjusts according to the body's requirements. If the iron stores are adequate, Typically, only about 14 to 18% of the dietary iron is absorbed. However, if there's a high need, such as in cases where you're deficient or maybe you're going through a period of growth, the absorption rate can increase to anywhere from 35 to 40%. Now, again, it depends on what form. If you're talking about heme iron that you find in animal products, it's absorbed efficiently, whereas non-heme iron isn't. And so that's influenced by the hemoglobin and myoglobin in the diet, which you get, again, from eating animal products. Non-heme iron, again, from plant-based sources, the absorption of that is less efficient due to the presence of other dietary compounds that might inhibit its uptake, like phytates or polyphenols and fiber. All right. There are certain ways that you can enhance the absorption. So meat protein factor, the presence of meat, fish, or poultry in the diet can enhance the absorption of non-heme iron. This is attributed to a specific factor in meat proteins that promotes iron uptake. And also vitamin C. If you consume vitamin C alongside non-heme iron, that'll boost its absorption. Vitamin C converts iron into a form that's more easily absorbed by the body. That's particularly helpful when consuming meals that might be rich in that plant-based iron. Here's just a table that shows various factors that might affect your iron absorption. Iron is a nutrient of public health concern. Even mild to moderate deficiency in iron can result in a compromised immune system. And as you can see, the progression of iron deficiency can be quite problematic, even leading to iron deficiency anemia. Here you can actually see two blood smears, one of them showing iron deficiency anemia on slide B. You can tell that because the red blood cells are smaller and they are paler, and that's an indication of iron deficiency anemia. The upper level is set at 45 milligrams per day. Above this, you might get some symptoms like nausea, vomiting, and stomach irritation, leading to diarrhea, and also impaired absorption of other minerals can occur. Okay, moving on to zinc. Food sources of zinc include meats and seafood and whole grain breads, except if those whole grain breads are unleavened, sorry, which unleavened breads are breads made without a rising substance like yeast, so like flatbreads, that can actually decrease zinc's bioavailability. Why is zinc so important is because it's an important cofactor for over 300 enzymes. Just one I'll talk about is superoxide dismutase. That's an enzyme system that helps the body eradicate free radicals. Free radicals can damage all kinds of tissues, so very important that we have superoxide dismutase. And if you don't have zinc, you can't have that. So that's why it's so important that you intake a proper level of zinc. Here you might see a list of symptoms that are indicating zinc deficiency. Just something to point out here, the upper level of zinc intake is set at 40 milligrams today, and you can go toxic in it. The symptoms are listed here, ranging again from rather mild to probably a little bit more severe, like impaired immune function and the inability to absorb copper. Amongst many unfounded claims of various supplements that may have very little to no clinical evidence, one thing we can certainly say is that zinc supplements have not been proven to prevent colds. This is something that you hear a lot. Again, no evidence of that at all. All right, now to copper. Food sources of copper include liver, shellfish, nuts, seeds, lentils, soy, and dark chocolate. If you need any excuse to eat some more dark chocolate, there it is. Copper is going to in function also as an important part or co-teammate or cofactor of enzymes. And one of the most important ones, again, to mention is that superoxide dismutase. Now, copper deficiency is rare, but it can occur, particularly in premature babies and malnourished infants, amongst the other things listed here. And what about toxicity? That's also rare, but it can be found, usually due to an accidental overdose in children or consumption of copper-contaminated items and something called Wilson disease. Wilson disease is also known as hepatolenticular degeneration, and it's a rare genetic disorder that causes copper to build up in the body, in the liver, brain, and eyes particularly, and that can, of course, damage those organs. Finally, we're on to the last item, vitamin K. Vitamin K is named for coagulation, the German word for coagulation with a C. And it's crucial for blood clotting, and it plays an important role in bone health. It is a lipid or fat soluble vitamin, meaning it requires fats for the proper absorption and transport within the body. There are a couple of different vitamin K members of the family. Phyloquinones or vitamin K1. This is the form of vitamin K1 that are vitamin K that you'd find in green leafy vegetables like spinach, kale, and broccoli. It's probably the main dietary form of vitamin K, and it's considered the most biologically active. And that is directly involved in blood coagulation. Menaquinones are the variant primarily obtained from fish oils and meats. It's also synthesized by bacteria in the large intestine. And vitamin K2 plays a significant role in bone metabolism by regulating calcium deposition. And that's going to promote bone formation and prevents calcification of arteries and other soft tissues. Again, why is it needed? We just talked about it, synthesizing of blood clots and also bone metabolizing. Now, where would you find it? This is just going to show you the various sources, but interestingly enough, 10% of it you are actually getting for free from the bacteria inside of your colon. But the remainder is going to come from food. Green leafy vegetables is like your most common source, but there are some other ones listed here. And these vitamins are stable in heat processing, but they can be destroyed by light. So typically you see these foods stored in darker or at least opaque packaging to avoid that. Here's just a graph showing the various food sources of vitamin K. Lots of green on that slide. 80% of that vitamin K in the diet is absorbed and incorporated into the chylomicrons. Menaquinones synthesized by bacteria are absorbed by passive diffusion. They're incorporated into lipoproteins for transportation, and they're excreted in bile. What about deficiency? Well, generally it's newborns that are at the highest risk for vitamin K deficiency, so they're given a shot of it right at birth. It's pretty rare among other age groups, but it can occur, particularly if you may be using antibiotics for a long time, wiping out that gut biota. And the last slide here is just going to let you know that vitamin K toxicity is pretty rare, considering that's a fat-soluble vitamin. And the reasoning for that is it's actually more readily excreted than other fat-soluble vitamins where you'd have to worry about toxicity a little bit more. All right, thanks for watching this video, and we will see you next time.